So we'll pick back up here with precipitation reactions. So directly related to solubility, you look at two compounds, and if they, or you look at your two separate things that you're adding to your aqueous solution, if those can combine in a way that makes one of them insoluble, then you will get a precipitate, and hence a precipitation reaction. So they form solids. Right? So we have those indicators of the phase for each type of thing. But yeah, precipitation reactions form a precipitate. We had some precipitation outside today. One of these, it's a very nice color, is potassium iodide mixed with lead nitrate. So you're adding this clear liquid into another clear liquid. That combination forms lead iodide, which is insoluble. And so you get this yellow, well, looks like a cloud, but it's a cloud of solid in the liquid. Generally speaking, if you mix two things together and it gets really cloudy like this, that's a solid. Right? So it's not going to drop in there and immediately form big chunks. Of course, you don't always get precipitation reactions. So in fact, most things, when you mix them together, you get nothing. Right? So you add one clear liquid to a clear liquid, and it still looks like a clear liquid. If you have a precipitate, again, it'll be some cloudiness, or it'll change colors. Yeah, I think you'll see that today, even. So the key to predicting if you get a precipitation reaction, right? Because now we've talked about you can recombine molecules together to form new molecules or new compounds. The next step is predicting from two reactants if you get a product. If you get a reaction, and in this case, if you get a precipitation reaction. So in a precipitation reaction are two solutions containing soluble compounds combine, and an insoluble compound precipitates. So it's only when you get something that's insoluble, a product that's insoluble, that you have a precipitation reaction. So this is the reaction from that previous slide with the yellow cloud. If we mix potassium iodide and lead nitrate, before we mix those, we have our two aqueous solutions. So we're homogeneous mixtures, right, with these separate ions inside. And when we mix those together, we have to consider what are the new combinations that we can get. Right? Because we know that our previous combinations are soluble. We can see them, they're clear liquids. So we can take our different ions, or cations and anions, and we can just write them out. So I'm just going to do K plus, I minus, PB2 plus, NO3 minus, and I'm pretty sure we're going to do this on the next slide again. And these I did roughly write out in the order that they were given previously. So one of our possible combinations would be potassium iodide. Another combination would be lead nitrate. Two nitrates because each nitrate has a 1 minus charge. Lead has a 2 plus charge. Oops, sorry, there's the 2. The other combination that we can get, and this is key, you can only have positives combining with negatives. So you won't get a positive-positive combination. You can't have potassium-lead. Doesn't work. Two positive charges, like charges repel. So you won't get this. So really what you're going to do is keep your cation and swap the anions. So we'll get potassium and nitrate and lead and iodine, or iodide in this case, I guess. So 2 iodides again because the lead has a 2 plus charge. And then we would look at all 4 of these and see if any of them is insoluble. So let me go to the next slide. So if you did go back and check, we can actually do that real quick because I bookmarked this, but I didn't bookmark the other one. There we go. So we can look at this, and we had potassium. Potassium is always soluble. So anything that forms with potassium is going to be soluble. Same with nitrate. So one of our combinations was potassium iodide. The other one was potassium nitrate. Both of those are going to be soluble. The other one we need to look at, or one of the other ones, is lead iodide. So if we have iodide here, generally soluble unless it's combined with lead. So that'll be insoluble. And I think the only other one I'm missing was the lead nitrate. But all nitrates are soluble. So we get lead iodide precipitating. Right, so that was that bright yellow cloud. The other ions just stay in solution. They don't form a solid, so they stay soluble. So if you want a formulaic approach to these kinds of problems, you write the formulas of the two compounds being mixed as reactants in your chemical equation. So for our previous example, that was potassium iodide plus lead nitrate. So those would be our reactants in our chemical equation. Below that equation, we'll rewrite the formulas of the ions, or below the equation, write the formulas of the ions. Don't exactly like the way that's worded, but I guess it includes nitrate. So we're going to rewrite these with the ions separated. So we're going to break these out. So potassium plus, I minus, whoops, plus lead 2 plus. And in some cases, if you're given just an equation like this, you'll have to infer the charge on lead based on the fact that it's combined with two nitrates, because lead is a transition metal that doesn't form a consistent charge. All right, so then we write all these out, and then we exchange the anions, rewrite the ion formulas below the product side. So like I said, we can't have potassium and lead won't form a compound together. So we can rewrite, just going to abbreviate here. All right, so we're exchanging the anions. So potassium was combined with iodide on the reactant side. On this side, it will be combined with nitrate. And then lead will combine with iodide. And I haven't written them as compound formulas yet. But now you would look at each pair and check against the solubility rules if one of them is soluble or one of them is insoluble, which we know that the lead iodide was insoluble. Oops, 2. So it forms a solid. The S in parentheses is solid, not soluble. But our potassium nitrate remains soluble, so it's still aqueous. So if both of those pairs are soluble, then you write no reaction. In this case, we have a reaction. Because if one or both of the new ion pairs is insoluble, write the formulas of the compounds after the arrow, and then we use AQ to indicate aqueous, or the soluble product. And to indicate an insoluble product, we use S for the solid. Once you've gotten to that, if you have a reaction, you need to balance everything without changing subscripts. Any questions at this point? Okay. As always, more examples. So when a solution of potassium hydroxide and nickel bromide are mixed, we're going to write a precipitation reaction if one occurs. So again, important to know those nomenclature rules. right, first step, write these out as the compounds. So potassium hydroxide. So potassium has a plus charge, and hydroxide has a 1 minus. And this is aqueous. And then nickel bromide. So nickel. And then here again, in parentheses, that Roman numeral 2 in parentheses, not 11, or II, indicates that we have a 2+ charge for nickel, because it is a transition metal without a consistent charge. And then bromide has a 1 minus charge. So that's the reactant side of our equation. And of course, if you wanted to, you could write out all the ions first, then proceed to balance their charges because they're ionic compounds, and then kind of skip the next step because you've already written them as ions. But following the rules that we just looked at, we now break these apart into their ions. So K plus, OH minus, and I2 plus, Br minus, and at this stage I am leaving off the subscripts, because we'll do all the balancing later using all the correct chemical formulas. At this stage, we just want to make sure that we're correctly swapping anions with their cations. So I always take the cations, right, those are the positive charges, and move them over in the same order. So K plus, that's going to be plus something, and then nickel, 2 plus the other anion. So on the left side, if we have potassium and hydroxide, we're going to swap the hydroxide over to nickel on the right side. So nickel hydroxide, and because we had bromine paired with nickel on the reactants, bromine will now be with potassium in the products. And then we can go check solubility rules. So we had potassium bromide. Let me write this a little differently because we haven't balanced any of this. Potassium plus bromide and nickel plus hydroxide. So potassium is actually in this list with no exceptions. So compounds of potassium are always soluble. Compounds of, because it's with bromide, that's going to be soluble. Nickel, usually the transition metals aren't on here except as exceptions. Weird sentence. So we'll look for hydroxide, which is generally insoluble unless it's paired with lithium, sodium, potassium, or ammonium. So since nickel is none of those, this compound is insoluble. So we do have a reaction. Now we can write these back on the actual product side, properly balanced according to their charges. So potassium bromide's easy. We have a +1 charge, 1 minus charge. So those are 1 to 1. And then for nickel and hydroxide, nickel has a 2 plus. Hydroxide is a 1 minus. So nickel, hydroxide. And now we get to balance it. So we don't have any free elements. Remember, free elements we want to balance last. And before those, we balance anything that's in 2 compounds on either side. We don't have either of those cases, so we can kind of start anywhere. I'm just going to start generally start on the left. So with potassium, so if we check potassium here and potassium on the right side, it's 1 to 1, those are balanced. Then I'll go to bromine. So bromine, there's 1 on the right, 2 on the left. So we're going to add a coefficient, the number in front, 2 for potassium bromide. Now we can go back and we can do potassium, or we can keep going forward and we'll come back to it eventually. But yeah, we can go back to potassium. So now we can do a 2 here. So we've got 2 potassiums, and that changed our number of hydroxides. So we've got 2 hydroxides on the reactants, but we also have 2 hydroxides on the products. And we have 1 nickel in the product, and we have 1 nickel on our reactants. So if you've been keeping track, we should be balanced. But we'll go ahead and go through these. With these polyatomic anions, you can write them as groups when you're counting, unless those groups break up, which won't happen very often. Nickel and bromine. So we have 2 potassiums, 2 hydroxides, 1 nickel, and 2 bromine. Then on the product side, again, 2 potassiums, 2 hydroxides, 1 nickel, and 2 bromines. So we predicted the products and balanced it. Oh, I should also write solid, aqueous. So I just added those, the AQ for the potassium bromide and the S for nickel hydroxide, because it is a solid. Are there any questions now? Nope? Okay. So now we'll write an equation for the precipitation reaction that occurs if any solutions of aluminum chloride and iron nitrate are mixed. Ammonium chloride. So if we have ammonium, is one of those pesky polyatomic ions, NH4+. I'm going to write it out this way this time. Get all the ions first. So chloride is Cl-. Iron, again, transition metal, so we're given the charge, 3+, plus nitrate, which is NO3-. So then for our reactant side here, we need to write these as properly balanced ionic compounds. So we get NH4Cl, both with 1 charge, and then iron. And since iron has a 3+ charge, how many nitrates do we need? 3. Yep. Okay. Now with that, we can actually just use this that we wrote up here, kind of like we did last time on the bottom. But we're going to take these cations and we're going to flip them. Or sorry, we're going to take the cations, we're going to move them over, and we're going to flip the anions. So ammonium's the first on the left. So put ammonium first over here. And again, that's going to be with the other anion and iron 3+ plus the other anion. So we just swap chlorine and nitrate. It's for such a, and I speak from personal experience on this, for such an easy concept of just swapping them, it's really easy to just move them over in the same order and think that you've swapped them. I've done it. So chlorine and ammonium were together on the products, so we want nitrate. And then we'll put chlorine in the other slot. And now we have to go back and check solubility rules. So again, our first compound here is ammonium chloride. I believe chloride does form some solids. So ammonium is always soluble. So the only one that we actually have to check for is the other, which is iron chloride. So again, cations generally aren't on here, but we have chlorine. When any of these ions, so it is soluble, and we don't have an exception for iron. So both of these are soluble. So it's no reaction. So as you get better at identifying these compounds by name and swapping those anions, these will go pretty quick if there's no reaction, right? Because it's kind of write everything down, swap the anions, see if you get a solid.
So when it's soluble, it's no reaction?
Right. Because if you think about, if you pour these two liquids together, in each of the liquids, they were separate ions floating around. When you pour them together, you just now have more ions in your solution, all still floating around, uncombined. You'll have a hell of a time separating them out, but they're not reacting. Okay, so another precipitation reaction, potentially, of potassium sulfate and strontium nitrate. So again, potassium and sulfate. Does anybody know the formula for sulfate? SO4, 2 minus. Strontium nitrate. Strontium, I don't know why, but rubidium, strontium, cesium, and barium, I always have to check. Someday I'll get them. Strontium and then nitrate, so NO3 minus. Move this over. So potentially here at this point, you could roll the dice, right? So you could write these down with the correct formulas, which you'll need later if there is a reaction. Or you could check at this point when I swap these. Right, so we're going to leave the cations in the same order. We'll swap our cations, or cations, same order, anions, swap. So potassium plus, well, was with sulfate, so it'll be with nitrate. Now strontium will be with sulfate. So we can go ahead and check now before we've even bothered writing these down with the correct formulas or balanced formulas. So potassium and nitrate are both always soluble. So we're only concerned here with sulfate. So sulfate is generally soluble, but we do have an exception. When sulfate pairs with strontium, barium, lead, and particularly lead 2, so lead 2 plus, you can't have lead 3 plus, would not apply to this exception. Or calcium 2 plus. So since we have strontium 2 plus, we do have a reaction. So now we have to write all of these with the correct formulas. So we get potassium, sulfate, and then we'll get strontium nitrate, leaving space for coefficients. And then potassium nitrate. Come on now. So bad about writing these. Aqueous. This is aqueous. And then strontium. Okay. Now we can start balancing. Does anybody want to pick where we start balancing? Potassium. All right, just go with the left anyway. So we got potassium, 2 potassiums, and we have 1 potassium on the product side. So we make that a 2. And then we now have 2 potassium, so we balance that. We have 2 nitrates on our products, and we have 2 nitrates in our reactants, so that's balanced. We have 1 strontium to 1 strontium, and then 1 sulfate to 1 sulfate. So they should all be balanced, but we'll double check it. Looks good there. Uh, 2 and 1, 1 and 2. So it's balanced. Easy 1 coefficient. Okay. Shifting gears a little bit here. This is kind of something we were already doing. So a molecular equation shows complete neutral formulas for every compound in the reaction. Complete ionic equations show aqueous ionic compounds as ions. So when we're writing complete ionic equations, separate only aqueous ionic compounds into their constituent ions. So if it's aqueous, if it's soluble, write it as ions. If it's insoluble, write it as a solid, as the compound. So for example, over here, this is aqueous, 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 and then this is solid. So essentially we would have all of this plus this as the solid. And that would be a complete ionic equation. So if it's solid, liquid, or gas, you don't separate those. Aqueous ionic compounds. After you've written your complete ionic equation, in fact, let me do this. So if I go through here and I say, yep. Oops. Put that guy there. And we would have, 2 and 2. And these would actually be 2 and 2 as well. So if this is our complete ionic equation, there are a lot of ions here that aren't participating in the reaction at all, right? Like I was saying, if you have a no reaction, you've got all these ions, they're just floating around, not interacting with each other. And that's what's happening here for most of the ions. So our spectator ions in our complete ionic equation are unchanged on both sides. So in this case, which colors show up on the screen even? Blue, does that look blue?
Yeah.
Close enough, some hesitance. Okay, so these ions that look the same would be, right, 2 potassiums, 2 potassiums, 2 nitrates, 2 nitrates. So they haven't changed from the left side to the right side. Position in the reaction doesn't really matter, or order. It can be rewritten any way. So we can omit those. We can just delete them from the equation. They don't matter. They're not reacting. So our reaction equation could be simplified into the net ionic equation. So we would just have SR2 plus SO4 2 minus reacts to form SO4 solid. So our net ionic equation, as opposed to the complete ionic equation, shows us just the species that are actually participating in a reaction. So just simplified. Brief summary. Molecular equation is the complete neutral formulas. The complete ionic equation is all of the species as they actually are in solution. And the net ionic is only the species that participate in a reaction.
Can you go back to the slide so I can see which one?
Okay. So we're given a reaction here, a balanced reaction. So we have some coefficients in there. I'm going to rewrite this as the complete ionic equation and then a net ionic equation for the reaction. So starting with the complete ionic equation, we'll take everything that's not a liquid, solid, or gas, and we'll break those apart into the constituent ions. So for hydrobromic acid, we'll have 2H plus 2 Br minus plus Ca calcium plus 2 OH minus and then water, our first product here, is a liquid, so we're going to leave that. It's a liquid. Then calcium bromide is aqueous, so it's going to be calcium 2 plus 2 Br minus. And I'm keeping here the number of each type of ion. Although you don't necessarily have to, but you will have to rebalance it. Sometimes you'll have to rebalance at the end. Okay, so that's our complete ionic equation. Which of these are our spectator ions?
The ones that are even?
The ones that are the same on both sides.
Yeah, same on both sides.
So which are those?
Bromine.
Yep,
And calcium.
and calcium. Yeah, so bromides, whoops. And the calcium 2 plus stay the same on both sides. So we'll get just 2H plus 2 OH minus is 2 H2O. And here, and this applies to any balanced reaction actually, if you get all even numbers like this, and you can simplify it, you can go ahead and simplify to the simpler equation, H plus OH minus H2O. Any questions? All right. So that was actually an acid-base reaction. We're going to talk about those. Brief definitions of acids and bases. We'll get into these more later, chapter 15, I think. But for now, acids tend to form H plus ions in solution. It's like we saw, if you have hydrobromic acid, when you add that to water, it's an ionic compound. It separates, dissociates into H plus Br minus. So we know it's an acid because of nomenclature, but also because they add H plus to solution. Easily recognized because their formula begins with hydrogen, which we covered in nomenclature. The protons taste sour. This is H plus is a proton, tastes sour. Sort of the opposites to acids are bases. And bases tend to form OH minus ions in solution. A lot of them are metal hydroxides. For example, KOH, potassium hydroxide, which I think is lye, used for canning. Right, makes a potassium ion and a hydroxide ion. They taste bitter and they feel slippery. So if we're ever doing a lab and you happen to get some base on your hands, you'll know that it feels slippery. Don't go and do that on purpose, but if it happens, you'll be okay, just rinse it off. But don't taste them. You can go have some Sour Patch Kids. Those have acid on them. So why they're sour. So we can react these acids and bases together in acid-base neutralization reactions. This is just a table of some more acids, some more bases, common ones. So can also be called neutralization reactions. They form water upon mixing because that H plus reacts with the OH minus and forms H2O. The other thing that comes out of that is called a salt. This is the chemistry term salt, not like table salt. Sodium chloride is a salt, but those remain dissolved in solution after the neutralization reaction. So if you write out the net ionic equation for these, it'll always be H plus OH minus H2O. I think it's the next slide, huh? Yeah, the assault rifle. All right. Good. Yes. Net ionic equation, like I said, is H plus OH minus gives you water. So you always have some acid, some base, water, and then a salt afterwards. So we're going to write a molecular and a net ionic equation for the reaction that occurs between H2SO4, or sulfuric acid, and potassium hydroxide. So H2SO4 aqueous plus potassium hydroxide, also aqueous. So you can kind of do the same thing here that we were doing with precipitation reactions, where you sort of leave the cations and swap the anions. In this case, or in the case of these acid reactions, acid-base reactions, one of our products is always going to be water. So you know this is an acid-base reaction because you have an acid and a base. For now, those will all be some metal cation with a hydroxide. So water is going to be one of these. And that's kind of taking the cation H plus here and combining it with the OH minus. It's not balanced yet, but our other product will be, so if we have H plus and SO4 2 minus, then we'll have this SO4 2 minus with the potassium on the right side. This will be K2SO4. And this is the liquid. This is aqueous. You could also do this by writing all of the, so you could go to a net ionic equation next. Or sorry, a complete ionic equation. Did kind of skip that step. Now we just need to balance it. So in this case, we do have an element, hydrogen, that's in 2 compounds on the left side. So we're going to wait to balance that until the end. Before that, though, we can look at, well, if we look at sulfate, that's balanced. And we don't want to balance hydrogen yet. So potassium is the next best candidate. So we need 2 KOH, potassium hydroxides. So we have 2 potassiums on either side. Now we can go ahead and check. So we have 1 oxygen in our from the hydroxide. Sorry, there's 1 in there times the 2 coefficient. So we need 2 oxygens on the right side, and I'm excluding the oxygens from sulfate because sulfate is an oxyanion, polyatomic ion. The number of oxygens there is not going to change. So you treat those, they're bound up, they're only going to move as a unit. So we only need to look at these oxygens, and we're going to find we need 2 of those. But now we can go back, because the only thing we haven't looked at yet really is hydrogen. So 2 times 2 is 4 hydrogens. Then we have 2 hydrogens here, and we have 2 hydrogens here. So 4 hydrogens on either side. Just to double check, I don't want to run out of space. Hydrogen, sulfate. Two. Looks balanced to me. Did I miss something? Do you have a question? Oh. Yeah, sulfate has a 2 minus charge. And potassium is a 1 plus charge. So you need 2 potassiums for each sulfate. Okay, we're not done yet though. We need a net ionic equation. And this is one of those spots where you could take a shortcut because this is an acid-base reaction. The net ionic equation for acid-base reactions is H plus OH minus is H2O. Acid-base or neutralization reaction. Either way. The other way you can do this is by going through the complete ionic equation. So we're going to take all of these, except for water, and we're going to dissociate them into their ions, or break them apart. So it's going to be 2H plus, SO4 2 minus, plus 2K plus 2OH minus. Leave water, 2H2O. And then we're going to have 2K plus SO4 2 minus. So that's our complete ionic equation. And now we can look at either side and identify our spectator ions. So those ions that do not participate in the reaction that are the same on both sides. So potassium and sulfate. And when we remove those from the reaction equation, that gives us the net ionic equation. 2H plus, or at least one step from it, because we can simplify this, because all of them have a coefficient of 2. So divide them all by 2. And we get that. Are there any questions now? Okay. Does anybody need more time on this slide?
Yes.
Yeah. Mm-hmm. Good?
What is it called at the end? The ionic, what is it called?
This is the net ionic equation. If you're familiar with like finance terms, it's kind of like your net income versus your gross income. The gross includes everything, the net subtracts out.
And then the other long one was the complete, huh?
Yeah, this is the complete. All right. So at this point, we've kind of covered most of the stuff. We're just going to talk about some more specific types of reactions. One of the ones I think is these are some of the more tricky reactions are the gas evolution reactions. So in a gas evolution reaction, well, some of them you get a gaseous product directly. So H2S is a gas, hydrogen sulfide. But other reactions form an intermediate product that decomposes into a gas. So you'll write out your products, and they react to form some set of products. Sorry, did I say products first? Reactants, and you'll get some set of products. And then there are some products, H2CO3 here, or carbonic acid, which can decompose into water and CO2, thereby giving you a gas. And then the sodium chloride doesn't react in that step, so it stays the same. The key for these is memorizing which things are gases or which things decompose into gases. There's not that many, but they're easy to forget about. The sulfides, hydrogen sulfide, that's the one that forms gases directly. So if you get something like this acid, hydrochloric acid, reacting with potassium sulfide, forms hydrogen sulfide, which is a gas. These other three go through intermediate reactions to form that final product that has a gas. So the one we saw was carbonic acid. The other ones are sulfites, so SO3. So we get, these are all reactions with an acid. So we get hydrochloric acid reacting with potassium sulfite, gives us an intermediate product, which isn't in this, the intermediates aren't in these examples. So we get this intermediate of sulfurous acid, and then that decomposes into water and SO2 gas, sulfur dioxide. The last one is, again, we have ammonia is the gas that's evolved. This is ammonium chloride reacting with the base this time. You'll get ammonium hydroxide as your intermediate, which can decompose into water and ammonia gas. So those are just kind of memorize or dedicate a little spot on your cheat sheet to those. So when you're writing an equation for these, you'll write your skeletal equation. That includes reactants, and then the immediate products that form. By swapping the anions on the cations, just like we did with precipitation reactions. Then recognizing if you have one of these four or one of these three at least, or if you get H2S, which is a gas directly. Then you balance the reaction. So we write a molecular equation for the gas evolution reaction that occurs when you mix hydrobromic acid. Again, got to know that nomenclature with potassium sulfite. So hydrobromic acid is HBr. That's aqueous. And potassium sulfite, K2SO3. So our skeletal reaction then is one where we just take the anions, we swap them with the cations. So we're going to have H2SO3, which this intermediate is aqueous, plus potassium bromide. Should have moved this over. And then at this point, you have to recognize that this is sulfurous acid, right? The H2SO3, it's a sulfite. So that's going to break down into SO2, which is a gas, and H2O, which is a liquid. And then you'll still have, because it ran out of space, KBr in solution. So your final reaction, you leave out that intermediate step and you write the reactants on the left side and your final products on the right side, or from the right side. So we're going to have, just copying this down, HBr. And then we'll have our final products of SO2, H2O, and potassium bromide. And at this point now you can balance it. And these are also like an exception to breaking apart things like sulfite. So now we want to consider sulfur and oxygen separately, because this doesn't go from sulfite on the left to sulfite on our, in the reactants to the products. It's SO2 now. So we can start with hydrogen, because it's only present in one compound. So we have two hydrogens on the right, one on the left. So it's 2 HBr. So now we can go and say, well, we got hydrogen balance, but now we need to balance bromide. So then we'll add a 2 there as well. So now bromide is balanced. We have to balance potassium. So 2 potassiums, 2 potassiums. I'm going to look at sulfur. We have 1 sulfur in the reactants, 1 in the products. And then oxygen, we have 3 in the reactants and a total of 3 in the products. Because ultimately it is the individual atoms that you want to balance. For all the other reactions, except oxidation reduction reactions, it's easier to leave them as groups in the case of polyatomic ions. Are there any question, gas evolution reactions? Nope.
Well, how is oxygen 3 too?
What?
You said oxygen, there's 3 oxygens there, and then where's the 3 oxygens over here?
3 here, 2 there,
Oh, yeah, okay.
1 there. Okay. Aha, oxidation reduction reactions. we'll cover this a little bit here, and then we'll cover it. The bit of chapter 16 that we're doing is for oxidation reduction reactions. They're also called redox, combining reduction and oxidation. Redox reactions are responsible for rusting of iron, bleaching of hair, production of electricity in batteries. Many but not all redox reactions involve something reacting with oxygen. Ultimately, redox reactions are the transfer of electrons. So there's a couple examples. So hydrogen reacting with oxygen. This is the reverse of that 9-volt battery and saltwater reaction. It's actually what powers the space shuttle. Not all space shuttles, but another one would be rusting iron. So iron reacting with oxygen. That's why it's called oxidation, because a lot of it happens with oxygen. Gives you iron oxide. Or combustion of natural gas, any burning is actually also a redox reaction, combustion. So methane with oxygen gives you CO2 and water. But water as a gas vapor. One example of one that does not involve, or a redox reaction that doesn't involve oxygen would be elemental sodium reacting with gaseous chlorine or elemental chlorine to make sodium chloride. And this is one of the important ones. A fundamental definition of oxidation is the loss of electrons. Fundamental definition of reduction is the gain of electrons. So oxidation is loss, reduction is gain. Oil rig. This is how I remember it to this very day. The other one is Leo goes grr, but I don't like that. It's too many. Oil rig. So oxidation and reduction must occur together. So if something loses electrons, those electrons have to go somewhere. So the substance losing them, oxidation is loss, losing electrons, oxidation, then another substance must be reduced or undergo reduction. This is a gain of electrons. For now, you just have to identify redox reactions. We're going to go over them on Thursday.
Is reduction like purification or something like that? Like refining metal?
Yeah, because if you can use reduction to purify metals. So if you have iron, I'm trying to think, because I think that burns the rust off. There's a really cool laser that you can use to burn the rust off of pieces of metal, but I don't think it directly turns the metal back into iron instead of iron oxide. But if you have iron being oxidized into rust, you can reduce it back into iron. I believe that's what the thermite reaction is. Yeah, we're going to go over those. We're going to go over these some more. So which of these are redox reactions? I actually think we're going to skip this because we're going to come back to it on Thursday. Somebody calling me? Yeah, combustion reactions are a type of redox reaction. Burning things, we're skipping, is that it? Yeah. We're going to skip oxidation reduction, come back to it on Thursday for chapter 16. So if you identify a chemical reaction, you have to be able to categorize it into the different types of reactions so you can properly predict what the products are going to be. So out of any chemical reaction, you can have a precipitation reaction, an acid-base reaction, gas evolution reaction, which can also be acid-base, or oxidation-reduction reactions. All right, like so many of the other things that we've done so far, it's just classifying things. move on in a second, but I just wanted to cover. So precipitation reactions form solids from liquids. Acid-base reactions are, if you have a H plus reacting with an OH minus. Gas evolution reactions form gases from liquids. I guess I should qualify here that this is really aqueous. And for now, just oxidation reactions are combustion reactions. Almost there. We can take this one step further by talking about what's happening with the atoms. So rather than classifying them by what type of product that we get out of it, we have these other types of reaction classifications. So you can have a synthesis or combination reaction. You're taking two separate things, combining them together, and getting a single product. It'd be like the iron rusting. Right? It's iron plus oxygen gives you iron oxide. A decomposition reaction would be like if you took this and reversed it. And so if we reduce that iron oxide to get back the iron, we get FeO2 and get iron plus oxygen. Displacement reaction, you're going to have one thing displacing another to form a new compound. And the most common one for this class is the double displacement reaction. That's where we're taking our cations and we're swapping the anions. So we have AB on the left, or AB and CD in our reactants. We end up with AD and CB in the products. So taking simple substances, combining them to form a more complex substance. Synthesis or combination, right? Substances combine. Specifically to get one product also. The decomposition reaction, we have a complex substance forms simpler substances. So if combination has one product, decomposition has one reactant. Just the one thing by itself breaking down. Oh yeah, here's the battery. So you can form, decomposing here, water into oxygen and hydrogen. Single displacement reactions would be one like, this is another redox reaction, but you're taking zinc and copper chloride and you're replacing the copper. It says copper chloride on the left, you're replacing that copper with zinc. So you end up with zinc chloride and then copper metal. You can actually use this for electroplating. So if you wanted to add a layer of gold to something. Electroplating is highly recommended over, used to use a gold mercury amalgam, and they would like paint it onto something and then shoot it with a torch, and the mercury would boil away. But what happens is you end up breathing a lot of that mercury. And that's why the Mad Hatter was mad, from breathing mercury. So sorry, that single displacement reactions, Mad Hatter. Then the double displacement reaction is where you have a lot of the, precipitation reactions are going to be double displacement reactions. You have two compounds, usually ionic compounds, swapping anions to get new products. All three of these, huh? Precipitation, acid base, and gas evolution. So those are going to be the most common. So again, it's just sort of a different way to classify things in terms of chemical reactions. So very quickly, for A, is it synthesis, decomposition, single displacement, double displacement? Single displacement. Because we have one thing and then one thing on the other side. For B, double. C, yep. And that really leaves one last thing. Cool. That's chapter 7. Thursday will be all about oxidation reduction.